Welcome back to Physics 141 online. I'd like to do an example problem now, which is a multi-step problem. It involves the conservation laws that we've been using in previous problems, but we have to use them together in this problem, and we have to think carefully about when we can use the law of conservation of momentum and when we can use the law of conservation of energy. So here's the problem. A mass m is given a slight nudge and slides down a frictionless hill of height h. At the bottom it collides with and sticks to a second mass, 2m, initially at rest. The two masses, because they stick together, they slide together up a second hill. Find the maximum height they reach. And this will be an answer, I've called it y final in the sketch, in terms of m, g, and h as needed. So, how do we tackle this problem? First of all, we realize it's a collision problem, and it's a special kind of collision problem. The collision is inelastic, and it's actually what we call totally inelastic, because the masses stick together. Since they stick together, that means energy is lost. And because some of the kinetic energy that was present before the collision is lost in the collision, then we have to use in that collision only the law of conservation of momentum. So, in order to answer this kind of a question, we're going to have to come up with a plan, and we're going to have step one, which is going to be, in order to analyze the collision, we have to find the velocity, we'll call it v1, of mass m just before the collision. So mass m sits on top of the hill, and it's going to slide down, and just before the collision we need to know what its speed is, because it's going to make a collision with the second mass, and we need to know what speed it's moving at when it hits. So since it's on top of a hill, in order to find out what speed it has at the bottom of the hill, then we will be using, in this step, the law of conservation of energy. Then, if we can find out what that velocity is, then we'll analyze the collision, and we'll be able to find what I'll call v2 of the combined system of m plus 2m, and this will be just after the collision. And since, as I said before, this is a collision that involves two masses sticking together, we will only use the law of conservation of momentum. And then the final step, now the two masses have stuck together, they're moving off at the bottom of the hill with a speed that I've called v2, then they begin to rise up the second hill, and eventually they'll reach a maximum height, and we want to find out that maximum height. I've called that y final, so we're going to find y final, and in some ways this is just the reverse of step number one, because we'll have this combined mass moving at a certain speed at the bottom of the hill, and it will make it up the hill to a certain point, and that point will be where the velocity of this combined system goes to zero. Because if the velocity goes to zero, that means it's reached as high as it will travel. So find y final of m plus 2m, this new system, and to do this we'll use, just like we did in step one, the law of conservation of energy. It helps me to break the problem down into these steps so I know where I'm going. And I'll need to use what I find in step one in order to solve step two. And then I'll need to know what I find in step two in order to solve for y final in step three. So I encourage you, when you have these complicated problems, you might sometimes have to draw several different sketches. So I'm going to draw a different sketch for each part of this problem. So for step one, you've got the mass at the top of the hill, and we want to know what speed it has at the bottom of the hill just before it makes the collision. So here's my mass m, starts off at the top, and since it's just barely given a slight nudge, we know that its initial velocity at the top is 0, and the velocity it has at the bottom I've chosen to call v1. We know the height of the hill, right, is height h, and so this is the relevant sketch in order to use the law of conservation of energy. So kinetic initial plus potential initial plus non-conservative work equals kinetic final plus potential final. Initial is at the top of the hill, final is at the bottom of the hill. There's no initial kinetic energy because we just give it a slight nudge, so it's so small that we're going to neglect it. If we measure the height from the bottom of the hill, the initial potential energy is mgh. There's no non-conservative work because there's no friction on this hill. Final kinetic energy is 1/2 m v1 squared, because that's the speed it has at the bottom of the hill. Final potential energy is 0 because it's at the bottom, and so we measure the height of the system from the bottom, so there's none there. And very quickly you can see if I divide both sides by m, that drops out, and if I solve for v1, I get that v1 is equal to the square root of 2gh. I'm not going to show all of the details there, but if you take that equation and solve for v1, that's what you'll get. So now we move on to step 2. Step 2, now we can just draw the situation at the bottom of the hill. So we've got our mass m moving at speed v1. It's going to strike 2m like this, so that's the before picture. The after picture, I'll just draw right below it, will be these two masses sticking together and moving off together to the right. So it's m and 2m, and if I just extend the surface a little bit, then the final velocity is what I've called v2. So I can use, as I mentioned up above, the law of conservation of momentum here. We'll call the x direction the direction to the right. And now here's where we add up the x components of all of the momentum terms before the collision and set that equal to the sum of all of the x components of momentum of all the different masses after the collision. So we have before and after. And this is easy. Before the collision, the only mass that has momentum is m. So m times v1, and it's moving in the positive direction, so that momentum component is positive. After the collision, the two masses stick together, so what we really have is m plus 2m, and they're both moving together at a speed v2. And what you really have here in parentheses is m plus 2m, that's 3m, so this becomes 3m v2. And now if I look at the left-hand side, mv1 and 3m v2, I can cancel the m by dividing both sides by m, and I get, as a result of this, that v2 is equal to 1/3 v1. And v1 I have from up here, so I'll go ahead and write this down over here, that v2 is 1/3 the square root of 2gh. So I've made great progress, and now I'm ready to solve for y final in step 3. In order to do this, I need to get a little bit more space, so I will erase some of the work at the top of the page up here so that I can fill in the work that I need to do in step 3, which will be another example of energy conservation. And so it's a pretty straightforward calculation, because I have at the bottom of the hill this combined mass 3m moving at a speed v2 that I know, and at the top of the hill, when it stops moving for just an instant, when it's at its maximum height, then I know that the velocity is 0, and therefore the kinetic energy is 0. So step 3, actually, I can draw here. Let me draw the picture down here for step 3, and then I'll have more room to do the work up above. So for step 3, the picture looks like this. You've got the two masses at the bottom of the hill, and then they're going to go up to the top to their maximum height. So here you have m and 2m together, and they're moving at a speed v2, and then this is just going to reproduce what I have in the sketch at the top. It'll have the two masses having come to rest at a height y final. So that's the picture that shows the initial and the final configurations of the two masses. And now up here, I'll go ahead and show the work. So remember, once again, kinetic initial plus potential initial plus work done by non-conservative forces is kinetic final plus potential final. Whoops. Let me fix that. Plus potential final. So kinetic initial, that's easy. It's 1/2. The combined mass is 3m. It's m plus 2m. And it's v2 squared. So I'll just write it as v2 squared, and I'll substitute in just a minute. What's the initial potential energy? It's 0, because at the bottom of the hill, there's no potential energy. There's no friction. So the non-conservative work term is 0. Now in the final, we know that when it reaches the maximum height, the kinetic energy is equal to 0. But the potential energy is now the mass, which is now 3m times g times the height, right? So this is 3m g times y final. All right, so what can I do with this? The two zeros are not important. I can divide both sides by m, so the m term is going to drop out, and there's a 3m on both sides of the equation. So the 3m drops out, and if I solve this for y final, I've got 1/2 v2 squared. I'm going to divide by g, so what I get is y final is equal to 1 over 2g times v2 squared. And so let me go ahead and now clear out a little bit more space by erasing this part. And all I need to do to get a final answer is substitute in my result for v2 from step 2 down here. I've got it at the bottom of the page, and substitute it in up here. I need to square it and substitute it in up here. So let's see, what do I get? I'm going to take v2. Whoops, I need to get my pen back. All right, I'm going to take the v2 expression from down here and substitute it all the way in up there. And I'm going to square it, so it's 1 over 2g, quantity 1/3, square root 2gh, all squared. All right, so that's going to be a 1/9. And then when you square root, you just get what's under the square root, right? So one more time, I need to clear out a little bit more space. And then we'll be just about finished here. We'll be able to assess our answer and see if it gives us something that is reasonable in terms of units. So y final is 1 over 2g, and then we've got a 1/9 because the 1/3 gets squared, and then we've got a 2gh, and look what happens. The 2's cancel, the g's cancel, and so we're left with just 1/9 h. So a very simple answer. It makes sense because we want a height, which is a distance, and here we have 1/9 the original height. It makes sense, if you think about it physically, that the combined system, which has more mass, will not go as high as the original mass was, but we probably couldn't have guessed the 1/9 without actually working through the problem. So, unit-wise, the units make sense, and it's less than y final is less than h, and that also makes physical sense. Beyond that, there's not too much more we can say. So, just go back and think about the problem again. Look at the 3 steps. We used conservation of energy to figure out how fast the mass falling down the hill would be moving right before it makes the collision with mass 2m. Then we used conservation of momentum to figure out what the combined masses, what their speed would be after the collision, and then knowing what that speed is, we looked in the third part and used conservation of energy to figure out the maximum height that they would rise to. So, you've got some homework problems like this, and I hope this helps you take apart a more complicated problem and break it down into smaller pieces that can easily be solved. I'll see you in class.